Welcome everybody to basically our third webinar in our SunEarth webinar series. This is part 2 of our introduction to commercial solar water heating. Um, so basically in this part 2, we're going to follow up on what we talked about earlier, and basically we're going to do a quick recap, basically make sure that everybody has all the stuff and information that they need to completely benefit from part 2. But basically we're going to do a deep dive into the design of the equipment, the sizing of the equipment, and some of the details that has to be paid attention to when trying to deploy solar thermal water heating. During the presentation, if you have any questions, please feel free to type them in the chat section, and then at the end of the presentation, we'll get back to all the questions and we try to answer as many as we can. In case we don't have enough information right away, or we need to do a bit of a research to get back to you, we'll make sure to get the contact information, and we'll get the information that you're asking for to you in a timely manner for sure. So I'm gonna basically do a quick introduction of SunEarth, who we are, for those of you who are in this call that don't know us. SunEarth's been around since 1978, and it's one of the largest solar thermal water heating equipment manufacturer in the world, and the largest in the Western Hemisphere. We are located in Fontana, California. We have 80,000 square feet of dedicated manufacturing space. The company has been 100% employee-owned since 2014, ensuring the continuation of services and equipment to our customers, current and future. To give you an understanding of SunEarth's contribution to the green industry, in the general sense, since 2010, 210 megawatt of energy that would have otherwise been spent on water heating basically was saved using SunEarth equipment and SunEarth solar thermal water heating equipment. So let's do a quick recap about what are we talking about when we talk about commercial solar thermal water heating. What are the applications? Basically, we are talking about whenever you have a large load that is year-round. Basically, that can be a multi-family residential building, mid-rise, high-rises, even low-rises, lodging facilities, hotels, motels, etc. Dormitories, medical facilities, hospitals, clinics, and all the stuff that they use large quantities of hot water all the time. Recreational facilities, commercial pools, especially indoor pools. We're going to talk about them because indoor pools, even when they are not being used by the public, because of the chemicals that are used in them, they need heating. So there is always that load there. And then lastly, we get to the industrial application. And with the industrial application, we're talking about process heating, pasteurization, anywhere that there is a large demand basically for heat. Solar thermal could be deployed to basically meet that requirement. When we're talking about solar thermal water heating systems, the major equipments that we're talking about is your solar array. Basically, you can see that here on the left. This can be roof mounted, as you can see here, ground mounted. Then there is a pump station or your control station, basically, that operates the entire system, operates the different pumps, basically based on differential temperature reading throughout the system. And there's always the storage. So when we're talking about solar thermal, there's always some type of storage, mainly depending on the application involved. Basically, because solar thermal water heating systems are designed to basically accumulate heat over time and dispense it on demand. So you need to have some sort of storage design and science according to the application that you're looking at. So these are the major components when we're talking about solar thermal systems. How they work. Solar thermal systems are always designed to work as a preheater to the auxiliary system, and this is what I mean as a preheater. Basically, whenever you're designing a solar thermal water heating system, you have to design an auxiliary system the normal way that you would have designed it. Basically, whatever heater that you're putting, if it's a gas, electric, whatever is your auxiliary or backup heater, it has to be sized to meet the entire demand of the building, just as you would have done it without the solar thermal. So once you introduce the solar thermal to this equation, it's basically continuously preheating the water before it goes to the main heater. So for example, if you have your main heater set at 140 degree Fahrenheit and you're feeding it water at 140 degree, the heater will not kick on. It will not basically start operating. If it starts receiving water at lower temperatures, let's say you have it at 140,
Hello.
Receives it at,
I am speaking.
I think we have someone's, yeah, we're good. So basically, if you receive the water at lower temperatures, the heater, your auxiliary heater, will only have to make up for those smaller delta T's. So basically, this is how the system is designed to reduce the load on the main heater. But why do we need to size the main heater or the auxiliary heater, excuse me, according to the entire load of the building? Is because uh, of convenience and comfort of the residents, or basically continuous uh, performance of the application. Because what if there's a week of clouds, or like we have here in California, but there's 2 weeks of smoke in the sky, basically reducing the performance of all solar systems, PV and thermal alike. So the auxiliary system has to be sized accordingly, and the solar is preheating the water, reducing the load on the auxiliary system. The interesting thing about solar thermal system, however, is they're extremely scalable. So if you think about it, the component that goes onto a single family residential, the main components are no different than the components that go on to a very large commercial project, such as the ones that we'll go over later on during this presentation. But the systems are extremely adaptable, extremely scalable. The larger the load that you have, the better the performance of the system. One thing to consider is the fuel that you're replacing, and this is a point that we'll go over and come back to over and over again. The more expensive the fuel that you're replacing with solar thermal, the better ROI you have. That's very simple because you get a certain amount of savings per BTU. The higher that number, the faster return of investment you will have on your system. So to go over a little bit of the terminology that we'll be using a lot, we're going to talk about the collector type. Basically, based on the demand that you have, the type of application that you're looking at, based on different factors, we decide between glazed panel and unglazed panels. So basically, the glazed panel can reach higher temperatures. Reason why is with the unglazed panel, as soon as you reach higher temperatures than the environmental temperature, you start losing the heat to the environment, so you cannot really reach higher than environmental temperatures. With a glazed panel, you're trapping the heat inside the box, basically enabling your system to achieve higher temperatures. Once that is decided, then we talk about what type of freeze protection and stagnation overheat protection we are looking at. You will notice that for our dear friends that use more direct system, freeze recirculation is not mentioned here as a freeze protection. That is definitely an option, a very good option to use in direct systems. But other than that, when we're talking about freeze protection and stagnation overheat protection, there are two main categories that we're looking at. It's either indirect glycol systems or a drain back system. In an indirect glycol system, basically, what is protecting you against the freezes is the mixture of propylene glycol and water in your solar loop. And for protecting the system against the stagnation overheat, especially, for example, if the systems are designed in colder climate areas where you need a lot of performance during the winter time, but you don't have that demand during the summertime, a certain type of heat dispensing mechanism has to be designed in order to prevent the systems from overheating too long, because overheating with glycol, those two really don't go well together. So that can create a lot of problems. So a proper heat dispensing mechanism has to be designed into the glycol system. For the drain back system, it's a little bit different. Basically, the entire fluid that you have in your solar loop will drain back to your solar drain back reservoir. That is basically the case when you reach certain high temperature limit or low temperature limit. So that's the same for your freeze protection and overheat protection. And it's very simple. Once you drain the entire loop into the reservoir, all you have left on your roof is some aluminum, some copper, and some glass. All three do very well under the sun, no problem. If you have fluid in the collectors, that's when you start encountering problems. So now we got that covered, let's talk about the main system designs. This is a diagram of a direct system. As you can see, the water comes directly from the city main, goes into the roof, gets heated, goes into the solar storage tank before being fed into the boiler or the water heater. This is a direct system. As I said, the freeze protection mechanisms on these are usually basically a recirc line, basically recirculating the hot water from the solar storage to the array during the nighttime when the temperatures drop to prevent freezing. And uh, one thing that you will notice in this system, because your everything is the same as your main water line, you have to use atmospheric storage tanks for the for direct systems. Moving on to the other two designs that we have. On the left over here, you will see the indirect glycol system. This unpressurized solar storage tank with external heat exchanger both on the load and the supply side. I'll get into the more detail about the information as we go further down the presentation. And on the right here, you have an indirect heat injection pump design into the system. This is by far one of the best designs available out there as far as cost effectiveness, the longevity of the design, and the reduction of the initial cost for commercial project. And we're going to go over this design in particular in more details for sure. So the question that now that we kind of went over all the information from our first part of the commercial series, now let's talk about why solar thermal. Why should it be used for this particular application of providing heat? First reason is direct conversion. Whenever you're directly converting one type of energy to another, you lose less efficiency. Every time you go through a conversion of energy, you lose some of your efficiency. For example, if you're to turn the solar energy into electrical energy and then use the electrical energy in the electrical water heater, you're converting your energy twice, and every time you're doing that conversion, you're losing some of your efficiency. So that's one thing that you have to consider. Another thing is the very high efficiency of the solar thermal water heating system. The collector by themselves, they have an efficiency of around 90%. And the systems in general speaking, when you take an average of all the systems that we have out there to look at it, the average efficiency of the entire solar water heating system is around 65%, which is pretty high. Solar thermal water heating systems been around for a very, very long time. From passive systems to active systems, they've all been deployed, tested, and basically improved upon. So the systems that now we have available are very reliable, and they can easily be deployed, and we know very well how they perform and how adaptable and scalable they are. As far as the cost effectiveness for providing BTU, for providing energy for the heating application, this is by far one of the most cost-effective solutions to begin with, and the cost effectiveness becomes, the ROI, basically what we're talking about earlier, becomes better and better the more expensive the fuel is. Depending on your location, that expensive fuel changes. In some areas, electricity is not cheap at all, and in some areas, electricity, for example, in Hawaii, electricity is extremely expensive. And then other type of, top of my head, propane, fuel oil, these are all expensive sources of fuel for heating. Another aspect that we talked about earlier was how we always have this need for an auxiliary unit. So when we know that we have to always match the systems up with something, we have to keep in mind the higher the COP of a system that we are matching up with, the higher the overall COP of the systems would be. So let's take this into consideration when we're designing the system. CPU is the COP, or coefficient of performance, of a typical boiler is about 0.85. So for every 1 unit of energy you put into the boiler, you get 0.85 of energy back. For a heat pump, the COP goes up to anything between 1.5 to 2.6. Sometimes it's even higher with the newer heat pumps. They go all the way up to 4. So for every 1 unit of energy you put in there, you get 4 units in return. But a correctly sized solar water heating system has an amazing COP of between 9 to 14 on average, and we're actually going to look at real life examples that even have higher COPs. So once you mix this two systems together to create what you need for your entire building, if you select the 2 high COP systems to work together, your overall COP will also be much higher. Solar water heating systems are never designed to meet the entire load of the building or the applications, and there's a reason for that. Is usually when we talk about solar fraction, which we'll get to during the next slides, if we try to go for more than 70% of the entire demand, again, this is very, very general and it does not apply to every case, but it usually the cost effectiveness aspect of it starts losing sense. So we have to, be mindful of how much load we're looking at, where the project is being deployed, what type of fuel that we're replacing. All that goes into the consideration before sizing the systems. And of course, there are 3 factors that we look at: how much roof space or array space you have available to begin with. It might be that you're really looking for a higher contribution from a solar thermal system, but you don't have the space for it. You don't have the space for the storage, or the main question that always comes up, the budget is not there to basically accommodate such a system. So those are the stuff that we take into consideration when we're designing a system. We talked about the COP of the solar thermal system. Here is a great example. This system is an actual real system that's been deployed in Massachusetts. The numbers are real. They all came from this great monitoring software called the Thermal Grid. So we can see basically the system performance at the bottom here. You'll see the solar loop runtime and the total energy consumed by the pump. So this is what you have to keep in mind, and this is why solar thermal has such a high COP. When you're operating a solar thermal water heating system, the main consumer of your energy is a pump. That's it. If it's a pressurized system, it's a correctly sized system, it's usually not a very large pump. So think about it. Running a pump is usually less expensive than running a compressor, for instance. So that's why the entire energy that was consumed by this pump during this 4,180 hours of operation was about 112 terms of energy, and the total energy produced by the system is 2,690 terms of energy. So when we put that 2 together, we get this COP of 24, which is, again, this is not a very usual system. This is a very unique system with an amazing design. But again, these COPs, these coefficients of performances, are absolutely possible within solar thermal. One concept that we talked about was the concept of solar fraction. What is solar fraction? When we talk about solar fraction, basically the solar fraction is a percentage of the heating that comes from your solar water heating system. So basically from the 100% consumption that you have, whatever is coming from solar, it's called solar fraction. The rest is provided by your backup system. So usually the solar fraction is one of the main aspects that we look at when we're trying to size a system and decide how many collectors you would need, what size of storage you would need, and those stuff. We look at solar fraction required for the project. So that changes a lot depending on the type of the building, the application, where the building is located at. If the building is going for any certain type of energy, basically certification, energy conservation certification, stuff like that, those all come to play. For example, if the building that you're designing is pursuing a LEED certification, you can get 2 LEED points if you achieve a solar fraction of 0.4 with your solar thermal water heating system, and you get 3 LEED points if you get 0.6 solar fraction when designing the system. For example, here in California, we have something called the Title 24 energy regulation, which looks at the total energy consumption of the building, and then based on that, certain energy conservation measures has to be taken. So, for example, if you're using if you're designing a multi-family building using the prescriptive method in California, it's very simple. You're looking at this 0.2 solar fraction. And now that we know what solar fraction is, let's talk about how we get to that solar fraction, how we size the system, how we design the system. First thing we need to do, you have to determine how much is your gallon per day consumption. What is your total daily hot water consumption? That goes through for every application, because whatever amount of energy that you're using translates to a delta T and a certain amount of water. Once we have that information, we can calculate the entire demand of the building. The demand for the building is not calculated the same way the boilers are calculated. This is the way we go about it, and the reason why we do this is because you get much more realistic system design as far as the size of the array and size of the storage is concerned. So once we know this demand, then basically this information can be fed into different softwares, calculators that are available out there, the simulation software such as F-Chart, the Title 24 calculator here in California. Polysun software is a great tool to design and basically design a system based on the solar fraction and the demand that you have. Once that information is available, it can easily be translated into something like this, which basically we look at the number of collector required to achieve a certain solar fraction. Here, this is an example of our F-chart report for a multi-family building. It was designed here in California Zone 13. So as you can see on the left here, we have the ASHRAE standard that tells us, okay, if you're designing a building, for example, if it's a multi-family residential between 2 to 20 units, you have to assume 42 gallon per day for water consumption. And then we get the local cold water data, and then the desired hot water temperature, and then we arrive easily to the daily demand. And from there, the information is fed to calculate the number of collectors needed to achieve a certain solar fraction. In this case, the solar fraction that they were looking for was above 50%, and it was achieved using 42 collectors to get about 55% solar fraction. Other aspect that you want to take into consideration when designing the system, obviously we talked about it, is how much space you have for the array and how many banks of collectors you can basically fit into the space available. Stuff that basically comes up is the number of collectors that you can put into a bank. Basically, there is a limitation on that based on the expansion that happens due to thermal expansion. Once the collectors start heating up, the system start heating up, it will expand, and that has to be taken into account. Also, the interruptions in the flow rate is another important aspect to always be mindful of, depending on the size of the header that you're using in your collector, and basically the sizes that is used in the main pipes for the building. So that has to be taken into account. So there is a certain number of the collectors that you can put into a single bank, and above that you have to start breaking them into second, third, and however many other rows that you need. Another aspect that comes into the designing of the array and the sizing of the array is how much shading you will get when you have multiple arrays configured one in front of another. So that's something that always comes into play and basically limits the amount of space that you have, because you cannot fit this one right behind the other. You have to leave enough room to make sure that during the winter time you still get enough sun to the arrays in the back for them to have a meaningful performance. One thing, we talked about different applications, and different applications have different demand patterns, different basically time of the days that they use the heat. For example, if you have a facility that uses a lot of hot water throughout the day, no matter what, and you have a limited space for the roof, you really don't want to think about too much about the storage because you have this huge load, you have a limited space for your array, so you will probably end up with a small solar fraction. Once you have a small solar fraction, which means you have a small contribution from your solar thermal system, means, and a large load, it means that the entire load is consumed, the entire contribution in whatever solar can produce will be consumed by that load. So there is no reason for you to start storing it. But in another application, when you have a large demand coming up at a certain time of the day, for example, if you have a facility that uses a lot of hot water for cleaning at the end of the day, for example, farms, dairy facilities, breweries, they use a lot of hot water for cleaning at the end of their shift. So what you wanted to do is design a system that can actually collect the heat throughout the day and have it ready for dispensation when the time comes. So now you have to design the proper storage accordingly. If you have a residential building and you know that in the morning time you will have a large demand, you want to basically design your storage and your array so you will have enough heat stored to carry you over the night into early hours of the morning until there is enough solar irradiance available for a solar thermal system to start performing. So we get back to this design that we talked about earlier, and I really do want to spend a little bit of time on this, talking about it. And this is basically an indirect drain back atmospheric design with a heat injection loop, basically. You will see that we have used an atmospheric tank here instead of an ASME tank, with several coils submerged into the tank for extracting the heat, and the collectors are connected directly to the storage tank itself, which is now doubling as your drain back reservoir as well. So what's happening here is the heat is being stored in the solar storage tank, and once you reach this target heat in the collector, or the high limit here on your array, or the low limit on your array, basically the entire loop will drain back into the main storage vessel. Here the heat is being extracted by 3 coiled heat exchangers submerged into this, and in order to avoid any pressure drops, we don't want to mess with buildings, main floor rates, any of that stuff, we have a heat injection pump here operated by your solar thermal controller, basically injecting the hot water back to the main loop that goes into your boiler. That way you don't have to be worried about any pressure drop. You don't have to compensate by adding a large number of coiled heat exchanger into your solar storage tank. Sometimes that is not available, that the space for that is not available to begin with. So that's something that you want to consider. In this design, there are more than few benefits, actually, because when you think about it, you have a drain back system that provides the maximum protection against both freezes and stagnation overheat. You have a heat injection solution that is basically eliminating the need for a huge number of heat exchangers, either coil or flat brazed plate heat exchangers, and you're replacing one of the most expensive, costly item, which is the ASME storage tank, with a much less expensive atmospheric storage vessel. And that by itself, other than reducing the initial cost of the system, you have to also take into account that when you have a non-pressurized vessel, you can heat the water in the vessel to higher temperatures without being worried about compromising the longevity of your tank, which means with the same footprint, with the same volume of water storage, you now have a higher capacity for heat storage because you're storing the same volume at a higher temperature. And by using a mixing valve, you can easily provide the target hot water to the building, but still relying on a larger volume of heat stored, basically. When we're talking about sizing the storage tank, there is a very easy formula. This is the general rule of thumb. Again, as I said, it depends a lot on the application, and it's something that you should definitely look into on project to project base, especially for commercial applications, especially if you're going out of realms of multifamily residential designs, stuff that are very, basically usual and common. Uh, it has to be studied, has to be looked into in details, but basically, uh, the formula that we use is we consider how much hot water can be heated by the array that is available in an hour to 160 degree, and then from that you do a quick calculation, which you get to the volume of the gallon that you need. That times the array size will give you the total storage volume that you need in gallons to get where you need to be. That V factor is something between 1 to 2, basically. So whatever the size of your array is in square feet, times that, the number is usually, again, as I said, between 1 to 2, will give you the entire storage volume required by your storage in gallon. So that's how you calculate that. Another aspect that I want to talk about is using more product in your design instead of using single items. Complete products can make everything much easier. We have to consider that as we are moving forward with the solar thermal industry, a lot of people who got into the industry in the early 70s, 80s are now, moving toward their retirement, and the new generation of plumbers, of professionals, of solar professionals out there, they would prefer something more user friendly, something more along the lines of, drop in, plug and play, uh, a ready to be deployed solution, something faster, something easier to work with. Basically, for many, many years, no matter how large the project was, when you had a solar thermal project, you had your solar contractor show up and start building the majority of the system from scratch, basically on the spot. So they would have the vessel, but everything else would have been assembled and programmed or whatever that had to be done to it on the job location. That's time consuming, and on top of that, it can lead to a lot of problems during your cold run, delays, stuff like that during the commissioning, which you don't like, especially now that everything is becoming more and more competitive and turnaround times are becoming more and more important. The faster you can get through a project and move on to the next project, it means more profit for everybody involved, the developer, the contractor, and the project owner. So what we can do is use complete solutions manufactured and they're ready to go. So we look at this example here. In this system that we have, you have a simple glycol system, the external heat exchanger for load and external heat exchanger for supply, which means both solar array is separated completely with one heat exchanger, and then a secondary heat exchanger is running between the solar heat exchanger and the potable water. So an extra degree of protection was created. Some jurisdictions do require designs like this or double wall heat exchangers, many stuff like that has to be taken into consideration as always. But for example, for this specific design, you can see all the pumps, all the valves, everything that they needed. If they wanted to buy everything from us and install it there by themselves, they could have absolutely done that. We have every single component that you see in this diagram, and they're available. But alternatively, what they can do is replace that entire section in the middle, this section here, with a solar station. And that's what I mean by simplifying it using SE products. Basically, we have now more than ever all these ready-to-go solutions that are designed for different applications, commercial, residential, and solar pool heating. These are basically products that have been manufactured based on the feedback that we have got from the market within the last 40 days, 40 some years of experience being in the market, and also our own research and development and acquisition of different products and the solutions available in the market. The result of all that effort resulted in this complete solutions that you can use instead of parts. This makes it easier on the designer, makes it easier on the installer, and also easier on the maintenance crew that has to deal with this large commercial systems in the future, because instead of parts and pieces, you have one piece of equipment that you have to deal with, one manufacturer that you have to deal with, and one basically warranty or user manual. Everything is now into that one piece of equipment. So this is what I mean by simplifying these designs. There are a lot of parts and pieces that go into, but you can avoid all of that by replacing it with a ready-made complete solution. I'm going to go over some of the case studies that we have. We don't have much time before we go to the Q&A part, but we're going to go quickly based on the applications that I was mentioning earlier. We're going to go over some of these. For example, here we have the Cavada Hotel in Los Angeles, California. The application that you see here is for domestic water heating. 36 TRB 40 collectors were used. And as you can see, a hotel, they always have a very large demand for hot water. They have cleaning, the laundry, all that stuff that they do on top of the usual consumption of hot water by guests, which we know for a fact that is usually higher when people stay at the hotels. They use hot water at a higher rate than they would at their own home. So there is that huge demand there, and it makes sense for them to take advantage of what's available out there, such as the federal tax credit or the CSI, California Solar Incentive Program, that was around until a month ago. They took advantage of that. That's another factor that you want to look at when you're designing the systems. What local rebates, what federal rebates, what tax credit, what incentives are available basically for the project owner to make that ROI better and better, make it more desirable for them to adopt a solution like this. But as you can see, the annual energy output of this system is about 95,000 kilowatt hour, which is really good. As I said, this is a system located in LA with really good solar irradiance, and they're using high performing TRB collectors. So that could be one of the main reasons why they're getting such a incredible energy output. This is another project that we did. This is basically a combi project application between domestic hot water and pool heating. They use 50 Empire collectors, and as you can see, the location change, the type of the collector change, resulted in difference in the output. So even though they have more collectors, the output is still low, but still incredible amount of energy provided for the specific. This is a wellness center, so they have a lot of different hot water uses, including all the therapy that they do, the hydrotherapies that they do, and other stuff, and of course domestic water heating. Multifamily commercial. This is a high-rise multifamily commercial done in Honolulu, Hawaii. This is a direct design system using 196 Empire EC40 high-performing collectors, and as you can see, an amazing energy output. Again, in areas that they have expensive fuel, such as Hawaii, Guam. Anywhere that fuel is expensive, it's much easier to find large commercial projects done with solar thermal, because the return of investment is so fast, and the amount of basically energy that you get for $1 per BTU is so good that justifying those projects are very easy. Another credible project that we've done, this is basically, instead of being one central system, this is basically smaller system being deployed throughout the facility. You can see the arrays popping up on different buildings. Each array was connected to its own solar storage, providing hot water to this units. Unfortunately, the last time I was trying to get the annual energy output for this specific project, I couldn't see them because I don't think the monitoring for them was still going on. But monitoring is one of the most important parts of the designs, and I think it's more and more coming to play, because nothing will show the building owner the benefit of their investment in solar thermal lifetime monitoring system, when you can show them that, during this month of June, for example, or month of July or August, you paid only close to nothing for solar water, for your water heaters, or for the entire hot water consumption in the building. And then, in the wintertime, you only paid for 30% of it or 40% of it, and the rest came from your initial investment in solar thermal water heating. This is another project in Canton, Massachusetts. This project was done using 40 of our smaller TRB 26 high-performing collectors, and the application was for an indoor pool. That was one of the applications that I was talking about earlier. They have these huge loads, and because of the chemicals that are used in the pool, they constantly have to heat the pool no matter what. Even if people don't go into the pool, they still need to be heated, and there is that large load there that is really good for solar water heating, to be deployed to meet some of that load, basically. So I think, yes, at this point, we're going to go over to our Q&A. Thank you so much again for joining us. I hope everybody's enjoyed it. I have some of the questions that you guys asked, so I'm going to go over them one by one. Joe was asking about the efficiency losses for double wall heat exchanger, for two heat exchanger design on both the supply and the demand side. And I don't know that top of my head. I don't know if you have the data or the data is available for that design, but you have to consider one thing. Whenever you're using brazed and plate heat exchanger, you're getting higher efficiencies than submerged coils. So there are definitely benefits with submerged coils. There are definitely benefits with brazed plate heat exchanger, but maybe the efficiency losses from using two brazed plate was made up for by the higher efficiency of the brazed plate heat exchangers themselves. But I can definitely look into more detail about the efficiency losses from using this specific design. And I know there are several of our contractors and our customers who specifically use this design, and I can get more information from them for sure. And the next question that we have from Olga. So she's asking how close do the panels need to be to the pump. Basically, the pumps are designed based on your distance. We would definitely prefer shorter distances using smaller pumps and lower consumption of energy. That's usually preferred. But no matter what, we had buildings that the design required for us to pump the water all the way from the basement 7 stories high, and the system and the pump station and everything was designed accordingly. So and there are other solutions. Again, for example, there is the rooftop drain back solutions, which the drain back reservoir is attached to the collector mounting system underneath the collector, eliminating the high head losses that would come from pumping all that water to the array on the roof. So there are different solutions to eliminate having to use larger pumps, stuff like that. But again, they need to be as close as your design allows them to be. If they can be placed closer, better. If not, you as a designer or assisting the designer, whoever is designing the building, they place it where they need to be placed, and then we'll figure out the pumping required accordingly. And last question that I have here is from Alex, and Alex wants to know more about solar thermal for dairies, and they have incredible potential for solar thermal because they have a huge load, both if they're doing on-site pasteurization, which I do believe they have to. I'm no expert in those facilities and how they operate, but if they have on-site pasteurization, and they have a huge heat demand, and then again for cleaning all that facility, cleaning everything that is used, all the equipment on top of the domestic hot water requirement, they have a huge load. So there's an incredible potential. A lot of time, these facilities, these dairies are not, located where there is natural gas available. So that's another factor. Natural gas is very cheap per term. So if that's not one of the options available, and they're using something more expensive, maybe solar thermal becomes even more and more interesting to them as a replacement for the fuel that they're using. So there is incredible potential there. If you have a certain project that you want to discuss in details, if you have some loads that you want to let me know, definitely send the information over. We'll go over it. We'll look at them. One thing that always is useful for us, if you have a building that is already built, do share the current water diagrams with us, whatever you have, and from there we can tell you what is the easiest, most cost-effective and beneficial way to integrate a solar thermal design into your building, basically. So awesome.
Amir, we've got one more question from Olga, and she wants to know if the panels can be used with existing tankless water systems, and can they be used to preheat boilers?
They can. Basically, you will have a storage that will act as a buffer and will provide hot water directly to either your boiler or your tankless water heater. So, for example, you set the temperature inside your tank. You have a mixing valve, especially if you have tankless water heater, gas-operated ones. We don't want to mess with the thermal fuse. So, what we have is we have the storage tank. Right after the storage tank, you put a mixing valve to make sure you're feeding it at 120 degree, 125 degree, wherever you want it. So the tankless would only come for those small delta T's. And as you know, tankless water heaters are incredibly efficient when they're dealing with those small delta T's that they need to make up for. So they work perfectly well with existing systems, of course. Yes.
I think that's it, unless there are any other questions.
I don't believe so. Is there? I don't see the chat, so. Oh, there it is.
Are there any further questions?
I think maybe Olga, somebody's typing something, so we'll wait. But while you're typing, I want to thank you all. Thank you so much again for taking the time. I hope you found this beneficial. I hope you will join us for the next webinars, which will probably be presented with 2 presenters next time, even more interesting and interactive. So these webinars will be on monthly basis. So we'll really appreciate you joining us for it. For areas that you have hurricanes, stuff like that, definitely that's understandable. But what we do and what we recommend is taking it again case by case, roof by roof. Every project is different. There are solutions that we offer. There are solutions that we have learned from our contractors and people using our equipment in those regions that they've adopted throughout the years to make sure that the collectors will stay securely on the roof. The collectors will withstand those high winds, speeds, stuff like that. So, and as far as having a specific insurance, I'm not sure, but there are so many solutions to make sure that the collectors are attached correctly and securely to your roof. We actually, it was really unfortunate to see the pictures, but it was really interesting. Last year when we had the hurricanes in Puerto Rico, we received an image from one of our contractors going out there to repair the equipment that was damaged from a roof. That the roof came off clear of the building. The roof was like probably 100 feet from the building, but the solar array was attached securely to the roof, which was the only silver lining for us to see in that picture. Was we have the solution to make sure the system is securely attached to those roofs. And are especially one other thing that you want to take into consideration is the different size of collectors that we offer. So we have collectors from 3x7 all the way to 4x10, and in the areas that you have higher winds, using a smaller footprint collector would be much more beneficial. So, for example, in Florida, in Puerto Rico, sometimes our recommendations would be, instead of using, a 4x10 collector, use two TRB-26s, which will give you almost the same footprint, but divided into smaller, units of footprint, so you have more resistance against the wind and stuff like that. But of course, these are all project based, case by case basis. So feel free to reach out to us, ask us as many questions as you like, send us your project design, send us your sketches, whatever you have, and we'll be more than happy to go over it with you. Of course, thank you all. Thank you for joining us. I really enjoyed sharing this information with you. Hope you guys found it useful. Please, you have my contact information. Feel free to shoot me an email, give me a call to talk about your next project or whatever design that you have in mind, or even if you have a solution that you want to know if it works or not. I'm more than glad to talk to you guys about it. Of course, definitely. I'll make sure I'll send a PDF copy of the presentation for sure.